All right, class, so this is the part 2, starting with 38. Why does lithium have a larger first ionization energy than sodium? That is because if we look at like the plus part, there we go. If we look at the plus part of lithium, like the nucleus there, and then we take a look, we have 2 electrons here in the first major energy level, and then lithium has 1 electron there. And we got the same thing here. Whoa, that's not what I'm looking for. There, I got 2 electrons there. Sodium has 8 electrons here, and then 1 electron on the outside. Now they both have 1 valence electron for the Bohr model, so you can see that. But why does it have a larger first ionization energy? First we have to know what ionization energy means. It means the amount of energy it takes to rip the outermost electron off. Notice there are things for an attraction between positive and negative. One of the main things is the distance between the 2 of them, and sodium has a larger distance, which means less attraction for that electron on the outside. So less attraction, number 1, less attraction, less attraction between charges. Because of greater distance. And the other part to that then is, of course, that here we have 10 electrons shielding the valence electron compared to only 2 electrons for lithium. Okay, so 2 electron shielding here for lithium, but 10 total shielding for sodium. So this one over here is sodium, and this one here is lithium. Okay, so that's why it's tougher to rip an electron off of lithium, because the distance is shorter, which means a stronger attraction to the nucleus, and we have less number of electrons shielding the positive attractiveness of the nucleus. So only 2 compared to 10. And greater distance for sodium means that that 1 electron is easier to rip off. Easier to rip off means lower ionization energy. Okay, the difference between the 3rd and the 4th ionization energies of scandium is much larger than the difference between the 3rd and 4th ionization for titanium. Explain why. Okay, so let's just take a quick look here. I think I have this one. Oop, so it's next. There we go. So let's do this. Let's go back here and take a look at the electron configurations. It's always the same reason for ionization energies. It always has to do with scandium's number 21. So let's take a look. That's going to be argon, like that, 4s2, 3d1. There it is. Okay, so the 3rd ionization energy would take away these 3, the 2 and the 4s and the 1 and the 3d. Okay, and then if you go to the 4th ionization energy, the 4th ionization energy would then take away 1 from argon. So once you take away a core electron, okay, takes much more energy. And how can you tell that it's a core electron? Take a look at the electron configuration. Scandium only has 3 valence electrons, so that means the 4th electron will have to come from argon, and that's why it's a core electron. Titanium, however, titanium is still argon like this. It's still 4s2, but in this case it's 3d2 because it's the second one over. So here I have 4 valence electrons before we get to a core electron. So I4 is still low in comparison in energy. Okay, and that's why, because the 4th electron that we're stealing from titanium still does not take from the core electrons in argon's electron configuration. Moving on. Why does lithium have a much larger second ionization energy than Be? Okay, so it's always the same, second ionization energy. What is lithium? Lithium's 1s2, 2s2, poop. I just keep going. 1s2, 2s1. But beryllium is 1s2, 2s2. Here's our core electrons, If I take 2 away, that leaves lithium, so I'm minus 2 electrons, that leaves lithium looking like hydrogen. Well, that doesn't make much sense because helium is what it wants to look like. But if I take 2 away from beryllium, then I'm left, come on, bonehead. Then I'm left with 1s2 for beryllium, and these are the core electrons, so that's okay. Core electrons for the second ionization energy. Okay, that's why. It's left. Core electrons are left. Let's keep moving. What is the trend in the first ionization energies as one proceeds down the group 7A elements? Explain how this trend relates to the variation in atomic radii. Okay, so 7A elements are fluorine, chlorine, bromine, and iodine. So as you go down, ionization energy should decrease. Okay, that's true not just for 7A, but it should be true for all of them. Because as you go down, you get larger and larger, and that extra electron on the outside, it's easier and easier to pull off. So it decreases because electrons, I should say, outside electrons are further away from nucleus. That says nuke. From nucleus and have more shielding from other electrons and have more shielding. There. That's why it's decreasing. Explain how this trend relates to the variation in atomic radii. So atomic radius also gets bigger. That's the whole point. Electron or ionization energy gets smaller or gets easier as the atom gets bigger. So it's like an inverse property. What is the trend in ionization energy as one moves across the fourth period from K to Kr? How does this trend compare with atomic sizes? As we increase, when we go from K to Kr, atomic radius decreases. Atomic radius decreases, which means the atom gets smaller and smaller, which means the outside electron gets tougher and tougher to pull off, which means that ionization energy increases. Okay? So again, IE goes up when atomic radius goes down. That's how it's working. Technically, it's more because not just the atomic radius, but the electron configurations of these elements are starting to get more and more stable. As soon as you get to the noble gas, it's the most stable configuration there is, which is why it's tougher to pull the electron off. Okay, and there's just some numbers to show you. Although I think that's it. Woohoo! All right, good. Finished with that.